Hi everybody, I hope you all had a great spring break or are in the midst of having a great spring break depending on when you watch this. So this lecture is meant to take the place of Tuesday's class since I am not in town this week. So I wanted to finish up our discussion of ring theory and get started talking about vector spaces and fields. So where I left you last time is we had this theorem that I mentioned but didn't have time at the end of class to prove. And the theorem essentially says that every principal ideal domain is a unique factorization domain. Alright, so remember a principal ideal domain is an integral domain where every ideal is principal generated by a single element. A unique factorization domain is an integral domain where every non-zero, non-unit element can be factored uniquely into irreducibles. And by uniquely, we mean if I factor it and you factor it into irreducibles, our lists of factors will only differ by units, if at all. Now to prove this theorem, we need a lemma, which is called the ascending chain condition. And please excuse my handwriting on the iPad, I know it's not good. Alright, so this lemma says that in a principal ideal domain, Alright, so at this point in the video, my sound stopped working, and so the rest of the video was recorded on mute. That was a lot of talking to nobody. But now I'm going back and trying to narrate over what I already wrote, so I apologize for any clunkiness. Anyway, back to what we were talking about. This lemma says, in a principal ideal domain, any strictly increasing chain of ideals must be finite in length. So if you've got one ideal contained in but not equal to the next ideal continuing, this is saying you can't go on forever in a principal ideal domain. Now, if you're not in a principal ideal domain, it's actually possible to construct a chain of ideals that goes on forever, but not in a principal ideal domain. So here's an example of a ring that's not a principal ideal domain, in which you do have an increasing chain of ideals that goes on forever. So let's let R be a subring of the polynomials with rational coefficients, and let it consist of just the polynomials where the constant term is an integer. So these are polynomials where the constant term is an integer and all the other coefficients can be any rational number. And you can check that this is in fact a subring of Qx, that it's closed under subtraction and multiplication. And here's an ideal, the ideal generated by 1/2 x. So these are all polynomials where there's not going to be any constant term because it's a multiple of 1/2 x. So the degree 1 term will be an integer times 1/2 x. And then the higher degree terms could be any rational coefficients there. So these are polynomials, no constant term. The linear term has a denominator of 2, or the denominator is a divisor of 2. If a1 is even, that could be an integer. So this is an ideal. You can check that this is an ideal of R. Similarly, you can have the ideal generated by 1/4 x. And that's the ideal where the linear term, the coefficient has a denominator that's a divisor of 4. Now this contains the first ideal that we started with, 1/2 x, but it's not equal to it. And similarly, we can talk about the ideal generated by 1/8 times x, or the ideal generated by 1/16 times x, and so on. And you could see how this chain could go on forever, where we're just kind of getting more and more expansive in what the denominator of our linear term might look like. So there's a violation of the ascending chain condition, which does not happen if we are in a principal ideal domain. That's what this lemma says. All right, so now how do we use this lemma to prove this theorem that every principal ideal domain is a unique factorization domain? we're going to need to prove that if we take an element that's not 0, not a unit, that it factors uniquely into irreducibles. And we're going to rely on this fact that we cannot form an infinite chain of ideals. So now let's go on and prove this theorem, that every principal ideal domain is a unique factorization domain. And I apologize for the awkward gaps. I'm re-recording the audio over the video, so hard to sync up. Alright, so let's prove our lemma first. Let's prove that ascending chain condition, and then we will talk about how to use that lemma to prove the theorem. So let's suppose we have an ascending chain of ideals, I1 contained in I2, and so on. And let's suppose that we are in a principal ideal domain. So our goal is to show that this chain eventually stops, that it cannot go on forever. So let's let I denote the union of all of these ideals. And you can check using an ideal test that I is in fact an ideal itself, just by showing that it's closed under subtraction and strong multiplication. Because we're in a principal ideal domain, we know that I then can be written as the set of all multiples of A, for some A in I. Now, since A is in I, that means A must be in one of these I sub n's. So let's say it's in I sub n for some n. Now what that means is, well, if A is in I sub n, then all the multiples of A are in I sub n. And I sub n is contained in I, because I is the union of all these i's. And that's equal to the ideal generated by A, which means that I sub n must equal I. And so I sub n must be the last term in this chain. You know, I sub n plus 1 is equal to in. And so the chain does not go on forever, and our lemma is complete. All right, so we just proved the ascending chain condition for principal ideal domains. On the next slide, we're going to show how we use that to prove our theorem that every principal ideal domain is a unique factorization domain. All right, so let's show that every principal ideal domain is a unique factorization domain using that lemma from the previous slide. So we're going to prove this in a few steps. The first step is we're going to show that if we have an element that's not 0, not a unit in our principal ideal domain, we're going to show that it has an irreducible factor, at least one factor that's irreducible. Remember, ultimately, our goal is to show that A can be factored entirely into irreducibles in a unique way. So first we show it has at least one irreducible factor. Now once we know A has an irreducible factor, we want to show that it has an irreducible factorization, that it can be factored entirely into irreducibles. Alright, so that establishes the existence of factorization. The last step is we need to show that this factorization is unique, up to units, meaning if I factor into irreducibles and you factor into irreducibles, our lists of irreducible factors every element on my list will be an associate of an element on your list. All right, so those are the 3 steps of our proof. Let's start with that first step, showing that A, if it's not a unit and not 0, then it has an irreducible factor. All right, so if A is irreducible already, then we're done. It's its own irreducible factor. So let's suppose A is reducible. If it's reducible, then we can write it as a product of 2 non-units, say A1 times B1. Now, if A1 is irreducible, then we're done. We found ourselves an irreducible factor. So let's suppose, what if A1 is reducible? Then we can repeat this process with A1. If A1 is reducible, then we can write A1 as, say, A2 times B2, where again A2 and B2 are not units. Then if A2 is irreducible, we're done. If not, we continue and write A2 as A3 times B3, and so on. And we can continue in this way until we find an A sub n that is irreducible. Now, we will eventually find an AN that is irreducible, because if we could just go on forever like this and never find an irreducible A, then we could build for ourselves an infinite chain of ideals generated by these A's, and that would be a contradiction to our lemma, to our ascending chain condition. So since A is a multiple of A1, every multiple of A is also a multiple of A1, so the ideal generated by A is contained in the ideal generated by A1. And similarly, since A and A1 are not associates, these 2 ideals aren't equal, so this is in fact a strictly increasing chain. And we can do the same thing with A1 and A2. Every multiple of A1 is also a multiple of A2, so the ideal generated by A1 is contained in the ideal generated by A2, and so on. So we must eventually hit an irreducible factor, because if not, we could continue this chain forever, which we know by our lemma is impossible. So AN is our irreducible factor. So we've now established the fact that we have at least one irreducible factor, because otherwise we would have a contradiction to our lemma. Alright, so on the next slide we'll show step 2, that A has a complete factorization into irreducibles. Alright, so step 2. Now, we know that A has an irreducible factor, so now we have to show that it can be factored completely. So, alright, A has an irreducible factor, let's call that irreducible factor P1. So then we can write A1 as P1 times something, call that something C1. So we're here, P1 is irreducible, and C is just any non-unit. Maybe reducible, maybe not. If C1 is irreducible, then we have ourselves a factorization into irreducibles, and we are done. Otherwise, if C1 is reducible, then we can repeat this process with C1. We know C1 has an irreducible factor, call that irreducible factor P2. Then we can write C1 as P2 times C2. Now we look at C2. If C2 is irreducible, then we're done. If not, we continue, and we write C2 as P3 times C3, where P3 is irreducible. And we repeat this process until we find an irreducible C. And for the same reason as before, we must eventually find an irreducible C, because if we didn't, we could form from these C values an ascending chain of ideals that goes on forever. So eventually Cn is irreducible, which means we can write A as P1 times P2 times P3 times everything up to Pn and then Cn. And that's a factorization of A into irreducibles. Alright, so that completes step 2. We know that every non-unit, non-zero element of our principal ideal domain can be factored into irreducibles. And now we just need to show that that factorization is unique. So down here I'm just writing down the ascending chain condition that would be violated if the chain of C's was reducible forever. So we've got ourselves an irreducible factorization. Let's show that that irreducible factorization is in fact unique. So we're going to suppose we've got two different factorizations into irreducibles and see what we can do with that. Alright, so for the last part of our proof, the uniqueness part. So let's suppose we have an element A, not a unit, not zero, and that we have two different factorizations of A into irreducibles. So on the one hand, we can say A is P1 times P2 times, say, everything up to PR. Stylus is not great with the dot dot dots. And let's say we have another factorization into irreducibles, Q1 through QS. So all these P's and Q's are irreducible. And we want to show that these two factorizations are the same up to units. So we want to show that each P on the left-hand side is an associate to a Q on the right-hand side. All right. So how are we going to prove this? We're going to prove this by induction. And the thing that we are going to induct on is R, the number of irreducible factors on the left there. So for our base case, we'll start with R equals 1. If R equals 1, then A just equals P1. A is already irreducible. And so on the right-hand side, it would have to just equal Q1, because it's irreducible, so it can only have one irreducible factor. And P1 and Q1 have to be equal, because they're both equal to A. So sort of trivially, but the base case, if A is already irreducible, then that factorization is unique. All right, so for our inductive step, we're going to assume that anytime we have a product of fewer than R irreducible factors, that that factorization is unique in the way we talked about earlier. And then we are going to try to use that hypothesis to show that the factorization we have here is unique. So we're going to assume anytime we have fewer than R irreducibles, the factorization is unique, and we need to show that it's true when we have a product of R irreducibles. So we want to take that product of R things and somehow reduce it to a case where we have one less. So in particular, let's look at P1. P1 is a divisor then of what's on the right-hand side, Q1 through QS. And we're in a principal ideal domain where we've already established the fact that irreducible means the same thing as prime. Now that's not always true. Those two terms are not always interchangeable. We saw examples of irreducibles that aren't prime in other rings, but in principal ideal domains, those two notions are equivalent. So we know P1 is irreducible by assumption, so that means P1 is prime. So it has the property that if it divides a product of elements, like it does here, then it must divide one of those elements. So P1 must divide one of these Q's, and let's just say that is Q1, since we can just relabel these, reorder these if we want. So P1 is a divisor of Q1. Now Q1 is irreducible, so the only way P1 can be a divisor of Q1 is if P1 is either equal to Q1 or Q1 is equal to P1 times a unit. That's the only possibility there. So that means P1 and Q1 are associates of each other. And in fact, we can even substitute P1 times U in for Q1 and then cancel P1 on both sides of the equation up above, which is what we're going to do on the next slide. Okay, so let me write down what we have. P1 through PR equals Q1 through QS. And now we know that P1 divides Q1, so we can replace Q1 with P1 times U. Now when we do that, we get P1 through PR on the left, and that's equal to P1 times U times the rest of these Q's. All right, and we can cancel out the P1. Since we're in an integral domain, we have the cancellation property. And now what do we have? We have ourselves a product of R minus 1 irreducibles. So we can use our inductive hypothesis. On the right-hand side, we have a product of S minus 1 irreducibles. Our inductive hypothesis says that this factorization must be unique. And so overall, then, our original factorization must be unique because all we did was cancel out a P1 on both sides, which are equal. And that establishes what we want, that we do have unique factorization into irreducibles whenever we are in a principal ideal domain. And we're done. All right, so one corollary of this theorem that we've got here is that everything that we know now is a principal ideal domain must be a unique factorization domain. So we already know the integers is a unique factorization domain. Another set of rings that we know are principal ideal domains are polynomial rings over fields. So now we know those are all unique factorization domains as well because we already know they're principal ideal domains. So every principal ideal domain is a unique factorization domain. Every unique factorization domain is an integral domain. And none of these go in the other direction. None of these are equivalent. So we saw that last time at the end of class last week. So often, to show that something is a unique factorization domain, we'll show something stronger, like that it's a principal ideal domain, or that it's what we call a Euclidean domain, which is our next and I think final category of rings that we are going to discuss in this unit on ring theory before we move on to fields next class. So Euclidean domains, I'll give you a formal definition of what that means, but it's going to fit on the far left of our spectrum here. So it's going to be the most restrictive, narrowest definition, but also have the most structure. So a Euclidean domain, which I'm often going to abbreviate with ED, this is an integral domain. Essentially, it's an integral domain where you have a version of the Euclidean algorithm or the division algorithm. So to make that precise, it means that there exists a function that we call the measure, which roughly measures the size of an element in your ring. And if you have a notion of size, then you can do the division algorithm because you can talk about a remainder being smaller than the number you started with, according to this function. So this function, we'll call it D. It'll be a function where when you plug in any non-zero element of your domain, so that little star means non-zero, and it outputs a non-negative integer. So by n there for natural numbers, I mean 0, 1, 2, 3, 4, etc. All right, so this function needs to have a couple of properties in order to be a good function to measure the size of an element. One property that we want it to have is that d of a should be less than or equal to d of ab for any a and b that are not 0 in our domain. And the second one, the most important one, is that we can do a version of the division algorithm. So if we have two elements, a and b is not 0, then we can always write a as b times q plus r for some q and r and d. And r has the important property that either r is 0 or the measure of r is less than the measure of b. So the remainder is in some sense smaller than the b value that we started with. So I'm going to write that over here in this box since I'm out of space otherwise. So dr needs to be less than db, or r needs to be 0. All right, so that's our definition of a Euclidean domain. On the next slide, we'll do some examples, and then we'll prove that it does in fact fit on the far left edge of this chain of inclusions. All right, so some examples of Euclidean domains that we've already seen. So any space where we've done some version of the division algorithm is a Euclidean domain. So one example is the integers. We know we can do the Euclidean algorithm with integers. So what's our measure function there? It's just the absolute value. So the remainder, the absolute value of the remainder is always smaller than the absolute value of what we started with. We also saw we could do a division algorithm in polynomial rings with coefficients in a field, where there the measure function was just the degree of the polynomial. If we divide two polynomials, the remainder is always a polynomial of smaller degree than the polynomials that we started with. So that's another example of the whole family of Euclidean domains. The next example that we will see and that we will prove is a Euclidean domain is the Gaussian integers. So that is a plus bi, where a and b are integers. So to establish that this is a Euclidean domain, we need a measure function, and our measure function here will just be the norm that we talked about last week. So the norm is a squared plus b squared. So we'll show that this function satisfies the properties. So the first one comes from the fact that the norm is multiplicative. The norm of xy is the norm of x times the norm of y. And if y is not 0, then the norm of y is at least 1. So the norm of x times the norm of y is at least as big as the norm of x. So that was the first condition in the definition of a Euclidean domain. The second one was that we can do a division algorithm. We can write x as y times q plus r, where the norm of r is less than the norm of y. So on the next slide, we'll do an example, an explicit example of this, and then after that, we'll prove that we can do it in general. All right, so let's look at an explicit example of just how we do the division algorithm with Gaussian integers. So let's let x be 3 plus 4i and y be 2 minus 2i. And our goal is to write x as yq plus r, where the norm of r is less than the norm of y. So basically we want to divide x by y to get our quotient. So let's start by just dividing x by y and see what we get. So 3 plus 4i divided by 2 minus 2i. To get that in the form something plus something times I, we need to multiply by the conjugate of our denominator, 2 plus 2i on the top and bottom. And then when we multiply that all out on the bottom, we get 2 times 2 is 4, minus 4i squared, so that's an 8. Up top, we expand everything, we get 6, minus 8, plus 8i plus 6i. So that 6 minus 8 is negative 2 over 8 is negative 1/4. 14i over 8 is 7i over 4. All right, so that's our quotient, but it's not an element of the Gaussian integers. So what we need to do to find q is to find the nearest integer to that, sort of the closest integer to what the actual quotient is, and then the difference between our actual quotient and our integer approximation will determine our remainder. So the closest integer to negative 1/4 is 0. The closest integer to 7/4 is 2. So we'll take q to be 0 plus 2i. All right. So then r is x minus y times q. So we can just fill that in and solve for r. 3 plus 4i minus 2i times 2i. Let's simplify that and see what we get. Distribute the 2i. We get plus 4i squared, which is minus 4. That's negative 1. So negative 1 is our remainder. And we can see that the norm of our remainder, the norm of negative 1, is just 1. And the norm of the y that we started with is 2 squared plus 2 squared is 8. So we did successfully find a remainder that is smaller than the y we started with in norm. And so we've satisfied the conditions of the division algorithm. So on the next slide, we are going to show that we can always do this. That given any two Gaussian integers, we can divide them, find our quotient, take the nearest integer, and then have that be our q, find our remainder, and show that the remainder always satisfies that inequality, no matter what we have for x and y. And that'll establish that we can do this division algorithm all the time, and therefore the Gaussian integers are a Euclidean domain. Alright, so we want to basically mimic the example that we did on the last slide, but do it more generally with any x and any y in the Gaussian integers. So let's say we have two Gaussian integers, x and y, and that y is not 0. Then x over y, that's something. Let's call it s plus t times I. Where here s and t are rational numbers, not necessarily integers. So this won't be able to serve as our q. So let's have m be the closest integer to s. And let's have n be the closest integer to t. Then we'll take q to be m plus ni. And that's sort of the closest we can get to the actual quotient. All right, well then we need to look at x minus y times q to get our remainder. Note that s minus m is less than a half, t minus n similarly less than a half, because every number is within 1/2 unit of an integer, every rational number. So we want to show that the norm of our remainder is less than the norm of y. So let's compute the remainder. All right, so the remainder is x minus q times y. And so that's equal to, you can check this, s minus m plus t minus ni times y. All right. Just think of x as x over y times y to get that there. And that first term, s minus m is less than 1/2, t minus n is less than 1/2. So the norm of s minus m plus t minus ni is less than 1/2 squared plus 1/2 squared. So the norm is multiplicative, so we're able to split it up like this. And if we can show that the norm of that first factor there is less than 1, then we'll have what we want. So that first norm is less than, as I said, 1/2 squared plus 1/2 squared. So I'm kind of running out of space, so I think I'm going to move up above to finish writing this. All right, so we need to show that this product is less than the norm of y. That's true because 1/2 squared plus 1/2 squared is 1/4 plus 1/4, 1/2, which is less than 1. So that does in fact establish that the norm of r is less than the norm of y, as desired. All right, and then here on this next slide, I just kind of flesh out what I ran out of space to do on the last slide. So since r is s minus m plus t minus ni times y, the norm of r can be split up in this way. S minus m is less than a half, t minus n is less than a half, so the norm is less than 1/4 plus 1/4, and we get norm of r less than norm of y. So the division algorithm works. Alright, so we showed that the Gaussian integers are a Euclidean domain. Next, we want to show that every Euclidean domain is a principal ideal domain. And so that Euclidean domains do fit on the far left edge of that chain of inclusions that we talked about earlier. Now this will be a strong theorem because that'll imply that anything we can show as a Euclidean domain is also a principal ideal domain and therefore is also a unique factorization domain. So oftentimes we'll show that something's a Euclidean domain as a way of showing that it has unique factorization. So to prove this, let's suppose D is a Euclidean domain. So it has a measure function. Let's call that measure function D. And we need to show that it's a principal ideal domain. So let's suppose we have an ideal, I. Let's say it's not 0. The 0 ideal is principal. We know that already. And our goal is to show that I is generated by some single element. Now when we showed that polynomial rings over fields were principal ideal domains, we took an element of the ideal of minimal degree and we showed that that was a generator for the ideal. We're going to do a similar thing here. We're going to take an element of I that has minimal measure. I'll call it A. So pick an element whose measure is the smallest of all the elements in I. Remember, the measure is always a non-negative integer, so we can always find a smallest one in our set. All right, so this means the measure of A is less than or equal to the measure of X for all X in I. All right, so A is something in I and it has the smallest measure, and we are going to try to show that I is generated by A. So to do that, let's take any other element in I and prove that it must be a multiple of A. All right, so suppose B is an element of I. All right, so our goal is to show that B is a multiple of A. Now we are in a Euclidean domain, so we have the division algorithm. So we can write B as A times Q plus R, where the measure of R is less than the measure of A, or R is 0. Those are our two options. So note that R is B minus A times Q. B and A are both in the ideal, and since the ideal is a ring, it's closed under multiplication, subtraction, that means R must be in our ideal. So if R is in our ideal, it can't have a smaller measure than A, because A was chosen to have minimal measure. So since the measure of R cannot be less than the measure of A, it must be the case that R is 0, which means that B is A times Q, which means that B is a multiple of A. So any element in I is a multiple of A, which means A generates the ideal, which is exactly what we were trying to show. So since I was just some arbitrary non-zero ideal, that means that every ideal is principal, and we have ourselves a principal ideal domain, which is what we were trying to prove. right, so let's look at an example of something that is not a Euclidean domain, but it is a principal ideal domain, just to show that those two conditions are not equivalent. So we proved that every principal ideal domain is, every Euclidean domain is a principal ideal domain, but it's not true that every principal ideal domain is a Euclidean domain. And here's our counterexample. Z with 1 plus the square root of negative 19 over 2. Now this is really hard to prove overall. Both steps of this is hard to prove. It's hard to prove that this is a principal ideal domain. It's hard to prove that this is not a Euclidean domain. There aren't any really easy examples to show that there are principal ideal domains that aren't Euclidean domains, but that is one of them. Now here's just one other theorem that the book mentions that I want to mention briefly but not prove, which is that if we have a unique factorization domain, then the polynomial ring defined over that UFD is also a UFD. And the proof is pretty much identical to the proof that we did in class to show that the polynomial ring over the integers had unique factorization. So if the coefficient ring has unique factorization, then the polynomial ring has unique factorization. All right, so I just want to end with one more example of a ring that is not a unique factorization domain and show that it's not. So let's look at Z with the square root of negative 13. Now, Z with the square root of most negative numbers is usually not a UFD. Some of them are, like we saw the Gaussian integers is a unique factorization domain. But remember here we have a norm, a squared plus 13b squared. And I'm going to show you two different factorizations for the number 22. So first let's note that the only units in this space are 1 and negative 1. Because remember the norm of a unit is 1, and the only way for a squared plus 13b squared to be 1 is if a is 1 or negative 1 and b is 0. So it's going to be very easy for us to see if two elements are associates of each other. So 22. 22 is 2 times 11, but it's also equal to 3 plus the square root of negative 13 times 3 minus the square root of negative 13. Now the norm of 2 is 4, the norm of 11 is 121, the norm of 3 plus or minus the square root of negative 13 is 9 plus 13, so that's 22. All right, so these are all irreducible because there are no elements of norm 2 or 11. So if something of norm 4 breaks down, it would have to break down into norm 2 and norm 2. If something of norm 121 broke down, its factors would have to have norm 11. If something of norm 22 were reducible, the factors would have to have norm 2 or 11. But if you look at our norm formula, a squared plus 13b squared, the only way that could equal 2 or 11 is if b is 0, otherwise the number is already too big. But if b is 0, then a squared would have to be 2 or 11. But 2 and 11 are not perfect squares. So there are no elements of norm 2 or 11, which means we can't factor this any further, and these are truly two different factorizations into irreducibles. And they are not associates of each other because the only units are positive or negative 1. So the only associate factorization of 2 times 11 would be negative 2 times negative 11. This other factorization is truly different. All right, so I think I'm going to end there. This completes our unit on ring theory. Where we're going to head for the rest of the semester is to start talking about fields. So in particular, what I want you to do before class on Thursday is read chapter 19 about vector spaces. This should hopefully mostly be a review from linear algebra. So hopefully nothing is unfamiliar to you there. It just reminds you, what a basis is, what it means for vectors to be linearly independent, and so on. So in the worksheet that I have planned for you for Thursday, there's going to be some questions about this ring theory stuff and also a few questions about vector spaces. So be sure to read that chapter before class on Thursday. So once again, I want to apologize for the clunkiness of this video. Like I said, I accidentally recorded pretty much the whole thing on mute and had to go back and redo it. So my voice probably wasn't always nicely synced up with the video of what I was writing, but I did my best, and hopefully it's all understandable. If you have any questions about anything in this video, please send me an email and I will be checking my email regularly and responding to them. Make sure you get your questions answered before you go to class on Thursday, so that on Thursday, when you go to class, I won't be there, but you guys will be working together on some problems. So you want to make sure you understand everything so you're well prepared to work on that. So again, I hope you had a great spring break. I hope your week back without me is going well, and I will see you all when I return next week. In the meantime, please contact me with any questions that you have. Have a good week.